created by MindSticks Foundation Trust. Good morning, students. Welcome to today's explainer lesson. I am absolutely thrilled to have you all here as we tackle a truly fascinating chapter in your science syllabus. Today, we're diving into the periodic classification of elements. We are going to unravel one of the greatest organizational puzzles in scientific history. So sit up straight, keep your notebooks ready, and let's get started.
Here is our agenda for today's class. We'll be moving through the classification need, Dobereiner's triads, Newland's octaves, Mendeleev's table, its merits and demerits, and we'll wrap up with the modern periodic law. Section 1. Classification need. Why organize elements? Imagine trying to find a specific textbook in a giant library where thousands of books are just dumped all over the floor. It would be total chaos, right? Well, in the year 1800, scientists only knew of about 30 elements. But today, 118 are known to the scientific world. To actually study this chaos and understand their distinct chemical properties, scientists desperately needed a pattern. But before we look at their solutions, let's use some brain power. Can you recall what we studied in our previous standards? What are the basic types of matter? Yes, solids, liquids, and gases. And what about the types of elements? Initially, we grouped them simply into metals and nonmetals, and later on we added metalloids. But as our knowledge kept increasing, this basic grouping just wasn't enough. We needed a much smarter system.
To give you a clear picture of how this evolved, we are going to follow a timeline. This is our roadmap of the brilliant scientific minds who attempted to solve this massive puzzle over the course of a century. We'll start in 1817 with Dobereiner, jump to 1866 with Newland's, explore Mendeleev's giant leap in 1869, and finally reach Moseley's ultimate breakthrough in 1913. So let's step back in time and meet our first historical guest teacher.
Section 2. Dobereiner's triads. The first pattern.
The year is 1817. A German scientist named Johann Wolfgang Dobereiner started noticing something very interesting. He was actually the first person to try and find a mathematical pattern connecting the properties of elements to their atomic masses. He created what he called triads. Now, I want you all to note down this important textbook definition. He made groups of 3 elements, which he called triads, that had similar chemical properties. He arranged these 3 elements in an increasing order of their atomic mass. And the crucial takeaway is this. He showed that the atomic mass of the middle element was approximately equal to the mean, or the average, of the atomic masses of the other 2 elements.
Let's walk through the math for his first triad to see how brilliantly this works. We have lithium, sodium, and potassium. Lithium has an atomic mass of 6.9. Potassium is 39.1. Now, if you add those together and divide by 2 to get the mathematical average, you get exactly 23.0. And guess what? The actual atomic mass of the middle element, sodium, is exactly 23.0. It's a perfect match. But as we know, science requires absolute consistency. The major problem here was that all the known elements at the time could not be classified into these neat little triads. The rules simply broke down for other elements, so the scientific search had to continue.
Section 3. Newland's octaves. The musical connection.
This brings us to the year 1866 and an English scientist named John Newlands. He actually found a connection between chemistry and, of all things, music. He arranged the elements known at that time in an increasing order of their atomic masses, starting with hydrogen and ending with thorium. And while doing this, he discovered a fascinating repetition. Please define this in your notes as Newland's law of octaves. When elements are arranged by increasing atomic mass, every 8th element has properties similar to those of the first.
Let's understand this mapping. Newlands compared this elemental repetition to the octaves we hear in music. In our Indian music system, we have the saptak notes sa, re, ga, ma, pa, dha, ni, and then the highest sa repeats again. In Western music, it's do, re, mi, fa, so, la, ti. Just like the 8th musical note perfectly repeats the first, the 8th element repeats the chemical properties of the first. For example, if you start counting from lithium, the 8th element is sodium, and they behave very similarly. Magnesium shows similarity to beryllium and chlorine to fluorine. It was a beautiful, poetic idea. But we have to ask, was it flawless?
Unfortunately, no. You must learn the limitations of Newland's law for your exams, so kindly pay attention here. First, this law was only applicable up to the element calcium.
After calcium, the eighth element simply did not possess properties similar to the first. Second, to aggressively fit elements into his table, Newlands placed two elements in a single box, like cobalt and nickel. Third, he placed elements with totally different properties under the exact same musical note. For instance, he put cobalt and nickel under the note do, alongside halogens, which makes absolutely no chemical sense. And finally, there was zero provision for newly discovered elements. Newlands' table was completely rigid.
Section 4. Mendeleev's table, the master blueprint.
Because of all those limitations, the scientific community needed a much more robust system. Enter the Russian scientist Dmitry Mendeleev. Between 1869 and 1872, he created a master blueprint that completely changed chemistry forever. He organized all 63 elements known at the time, and he considered the fundamental property of elements to be their atomic mass. Students, I need you to strictly memorize Mendeleev's periodic law. Properties of elements are a periodic function of their atomic masses. Simply put, this means that if you arrange elements by increasing atomic mass, their physical and chemical properties will repeat periodically.
Section 5. Merits and demerits. Evaluating Mendeleev. Now, Mendeleev's table was highly accepted globally, but as a science class, we must do an analytical textbook breakdown. Let's start with the merits. Mendeleev was an absolute visionary. First, the atomic masses of some elements were actually revised just to give them their proper place in his table. For example, beryllium's mass was corrected from 14.09 down to 9.4. Second, and this shows his incredible scientific foresight, he purposefully left vacant places in his table for elements that had not even been discovered yet. And third, when noble gases like helium and neon were discovered much later, he was able to create a zero group to fit them in perfectly without disturbing the rest of his original table at all.
To truly prove Mendeleev's genius to you, let's look at his specific prediction for an undiscovered element he temporarily named Eka aluminum. He boldly predicted its atomic mass would be 68, its density would be 5.9, and its melting point would be low. Years later, scientists actually discovered the element gallium. When you compare his predictions with the actual properties of gallium, it's mind-blowing. Actual mass, 69.7. Density, 5.94. Melting point, 30.2. His predictions matched almost exactly. It was a massive, triumphant moment for his periodic table.
But science is always progressive, and Mendeleev's table definitely had its demerits. Let's shift gears and understand the ambiguity that arises when you use atomic mass as your ultimate standard. First, cobalt and nickel have the exact same whole number atomic mass. So which one should come first? The sequence became very ambiguous. Second, when isotopes were discovered, which, if you recall, are atoms of the same element with the same chemical properties but different atomic masses, they posed a huge placement challenge. Where on Earth do you put them? Third, the rise in atomic mass from one element to the next is not uniform. Because it's not a steady, predictable jump, it became impossible to predict exactly how many elements could be discovered between two heavy elements.
And then, of course, there was the fourth demerit, hydrogen. Hydrogen acts exactly like a mischievous student in the classroom who wants to sit with two completely different groups of friends. On one hand, hydrogen shows deep similarities with the halogens in group 7. They both form diatomic molecules like H2 and Cl2. But simultaneously, hydrogen strongly resembles the alkali metals in group I, forming very similar compounds with oxygen and chlorine. Because of this frustrating dual personality, Mendeleev just could not decide on a fixed, correct position for hydrogen.
Section 6. Modern periodic law, the final solution.
Let's fast forward to the year 1913. An English scientist named Henry Moseley conducted some brilliant X-ray tube experiments and finally uncovered the interior secrets of the atom. He demonstrated that the most fundamental property of an element is actually not its atomic mass, but its atomic number, which we denote by the letter Z. The atomic number is simply the number of positive protons inside the nucleus. This was a crucial, game-changing shift. Therefore, the modern periodic law was officially stated. Please write this down and highlight it in your notes. Properties of elements are a periodic function of their atomic numbers. By simply organizing elements by their proton count, which goes up sequentially by exactly 1 every single time, the entire periodic table perfectly snapped into place.
This brilliant realization by Moseley brings us to the end of today's lesson module. But before I let you go, I have an engaging homework question for you to reflect upon. How exactly does classifying elements by their atomic number permanently resolve the mysteries and demerits left behind by Mendeleev? I want you to think about those isotopes we discussed and think about the cobalt and nickel placement issue. Write down your answers, and we will definitely discuss this at the start of our next class. Until then, keep studying hard, properly review your notes, and stay curious.
Thank you, class.